So let me start by recalling what we talked about yesterday. Okay. So recall that in chapter 2. Let's see. Okay. So in chapter 2, we showed that for both discrete and continuous time signals, you can always represent them as a linear combination of shifted impulses. So therefore, if you pass these signals through a linear time invariant system, then the output signal will then also be a linear combination of the responses of these shifted impulses with the same scaling parameter. Okay, so in this case, if you are able to obtain the impulse response of this linear time invariant system, you will be able to completely characterize the input and output relation of any signal. Right. Now, in this chapter, instead of using these delta functions, right, these shifted impulses as the basic signal components for representing, these input signals, we instead want to look at the use of these complex exponentials as the basic signal components. Okay, so we want to instead look at signals that can be represented using these complex exponentials as the basic signal components. Right. Now, the main motivation for doing this is that, is because these complex exponentials are eigenfunctions of linear time invariant systems. So what I mean by that is that if you take a complex exponential as the input, then what you get at the output will also be the same complex exponential, except for a scale that depends on the parameter s. Okay, so the reason for wanting to look at complex exponentials is because these functions are eigenfunctions of linear time invariant systems, meaning that if you input the signal, you will get the same thing at the output except for this additional constant in the front. Okay. Now this scale h of s, you can evaluate by taking the integral of the impulse response times the complex conjugate of the complex exponential that you're looking at. Okay, or similarly, in the discrete time case, when you're looking at this particular z here. Okay. Right. So then, if you say that this complex exponential yields a output that is the same complex exponential times this factor h of sk here, then if you input a linear combination of complex exponentials, then you would expect that you would get also a linear combination of the same complex exponentials, okay, with the same linear combining coefficients. Okay. So then, right. So then the question is, what type of signals can we actually represent in this form, right? So what types of signals can we actually represent in this form? If this set of signals that we can represent in this form is too small or occurs only in rare cases, then it probably would not be of interest to us, right? But it just so happens that a large class of signals, basically almost all of the signals that we may encounter in engineering applications may be represented in some form like this. Okay, so that's why this analysis is so practically interesting. Okay, so to gradually develop this idea, let us start out by looking at periodic signals. Okay, because we know that these complex exponentials, which are essentially sinusoids, right? They are periodic depending on the choice of the frequency. So if you take a linear combination of these complex exponentials, you would at least expect that they can represent something that is also periodic. Okay. So suppose we start out by looking at a signal that is periodic with period capital T, right? Meaning that x of t is equal to x of t plus capital T for all t. So here, the fundamental period is the smallest capital T, such that this equation holds, and then 2 pi over this fundamental period gives you the fundamental frequency. Let's call omega naught. Okay. So two basic examples of periodic signals with fundamental frequency omega naught are either the sinusoidal signal cosine omega naught t or the periodic complex exponential e to the j omega naught t. Okay. Now suppose we start by looking at this complex exponential e to the j omega naught t. Okay, so this is a periodic signal with period capital T. Okay, with period capital T. Now, if you take complex exponentials with integer multiples of this fundamental frequency, then you can construct other complex exponentials with the same period capital T. Okay. So if you collect all of these complex exponentials together, then what you have is a set of so-called harmonically related complex exponentials, right? So this is the set of complex exponentials with frequency equal to, the integer multiples of omega naught. Okay. So one interesting property of the set of harmonically related complex exponentials is that all of these signals are periodic with the same period, capital T. Okay. So therefore, if you take the linear combination of these complex exponentials, right? If you take the linear combination of these harmonically related complex exponentials, then this linear combination, let's call it signal x of t, must also be periodic with period capital T. Right? So all of these individual components are periodic with period capital T. So if you take the linear combination of them, they together will also be periodic with period T. Okay. So if you by choosing different choices of these linear combining coefficients, you can construct all different kinds of signals x of t. Okay. So, by the choice of these set of linear combinations is, uncountably infinite. So by just gathering the signals with all different choices of these linear combining coefficients, you essentially have, an infinitely large set of signals that can be constructed by taking linear combinations of these harmonically related complex exponentials. Okay, so this is saying that really a large set of signals can be represented in this form. So if you can represent a signal, by representing a signal of period t in this form, you say that this is in the form of a Fourier series representation. Okay, so by writing x of t in this form, you say that this is the Fourier series representation of x of t. Right. So going in this direction, right, starting out with the set of harmonically related complex exponentials. By taking all different kinds of linear combinations of these complex exponentials, you can construct a very large class of signals that can be expressed in terms of its Fourier series representation. Okay. Now, from the other direction, suppose that you are given a signal x of t, right, knowing that it has a Fourier series representation, then it would be necessary to know how to determine this expression, namely how to determine the coefficients for this linear combination. Okay. So this is what we talked about at the end of yesterday's lecture, right? So suppose that we are given a periodic signal x of t, okay, and we want to find its Fourier series representation. Right? Namely, we need to find the Fourier these linear combining coefficients ak. And how should we do that? Right. So through this derivation that we showed yesterday, we find that in order to find the coefficient for the nth term, right, the coefficient for the nth term or the kth term, the coefficient for the nth term corresponds to a complex exponential of e to the j n omega naught t. Okay. So to find the coefficient an, you take the average over the multiplication of x of t, the average over one period of the multiplication of x of t and the complex conjugate of the complex exponential that we're interested in. Okay. So namely, you take 1 over t, right, the average over one period, the integral 0 to capital T, x of t e to the minus j n omega naught t. Okay. Now, since this signal inside the integral is periodic with respect to period capital T, therefore, it doesn't really matter, what range you are taking this integral over, right? As long as this integral extends over an interval of length capital T, you should get the same result. Okay, so therefore, instead of specifying the upper and lower limit of this integral, right, we often just write this period capital T in the subscript to indicate that this integral is over an interval of length capital T, regardless of what is the starting point. Okay. Okay. So if you are given the linear combining coefficients, ak, you can then construct the signal x of t using this expression here. And vice versa, if you are given the signal x of t, then you can construct the Fourier coefficients ak by computing this integral here. Okay. So with xt, you can find ak, and with ak, you can find x of t. So this is a invertible relation. Okay. So this ak here is a Fourier series, is the so-called Fourier series coefficients, or is also sometimes called the spectral coefficients because it is the coefficient corresponding to the spectral component of x of t at frequency k times omega naught. Okay. All right. So let's look at a few examples. Okay. So what we gave here is a general expression for finding the linear combining coefficients or the Fourier series coefficients given the periodic signal x of t. Okay. Now, in some cases, it is pretty obvious by observation what these linear combining coefficients are. So if it is already obvious from the expression, then you do not necessarily have to apply this formula here. Okay. So a couple of examples of these, obvious cases. For example, in example 3.3, we have x of t equal to sine omega naught t. Okay. So directly by Euler's relation, you can write this as 1 over 2j e to the j omega naught t minus 1 over 2j e to the minus j omega naught t. Okay. So if you take e to the j omega naught t, subtract it with e to the minus j omega naught t, the real part cosine cancels out, and what remains is 2 times the imaginary part, which is j sine omega naught t. Okay, so 2j is, by dividing by 2j, you get rid of the coefficient in the front, and then what you remain is sine omega naught t. Right. So by this expression, it's evident what the Fourier series coefficients are. Okay, so these are the first order harmonics, right? These are the fundamental components. So here we can see that A1 is 1 over 2j. A sub minus 1 is minus 1 over 2j. And everything else is 0, right? So AK is 0 for all k not equal to plus or minus 1. Okay, so just by observation, we can find directly the Fourier coefficients in this case. Now this example 3.4 is similar, right? For all these sinusoids, sine, cosine, we can split them into complex exponentials using Euler's formula. Okay, so in particular, so for sine omega naught t, right, it's similar to what we have above here, which is 1 over 2j e to the j omega naught t minus e to the minus j omega naught t. Okay. Now for this term, 2 cosine omega naught t, we can write it as e to the j omega naught t plus e to the minus j omega naught t. Okay. Now for this cosine here, it's similar to the second term, but without the 2 in the front. So this becomes 1/2 e to the j 2 omega naught t plus pi over 4 plus e to the minus j 2 omega naught t plus pi over 4. Okay. All right, so then just by observation, we can find the coefficient A0, which corresponds to the constant term, should be 1. Okay. And then for A1 corresponds to the coefficient of the term e to the j omega naught t. Okay. So we have e to the j omega naught t here and also here. So A1 is 1 over 2j plus 1. Okay. Or you can sort of reorganize this. Right? If you multiply j in both the numerator and denominator of this, you will get 1 minus 1 over 2j. Okay. So similarly for a sub minus 1, we see this should be the coefficient for the term e to the minus j omega naught t. Okay. So this becomes minus 1 over 2j plus 1, right, which is 1 plus 1 over 2j. Okay. So furthermore, right, other than these fundamental components, right, we also have the second order harmonics here. So the coefficient corresponding to A2 is this 1/2 times e to the j pi over 4. Okay. So this can also be split into a factor in the front, which is e to the j pi over 4. Okay. So e to the j pi over 4 is cosine pi over 4. Right? Cosine pi over 4 is 1 over square root 2 plus j sine pi over 4, which is also 1 over square root 2. Okay, so this becomes square root 2 over 4 of 1 plus j. Okay, so similarly for this second order harmonic, e to the minus j2 omega naught t, the coefficient a minus 2 is 1/2 e to the minus j pi over 4. Okay, so if you evaluate this, this will become square root 2 over 4, 1 minus j. Okay, so by observation, in this example, you can directly obtain the Fourier series coefficients for a0, a plus or minus 1, and a plus or minus 2. Now, for all the other terms, the coefficients are 0. Okay, so ak is equal to 0 for all k not equal to 0, plus minus 1, and plus minus 2. Okay, so these are obvious examples. Now we can look at less obvious examples. Okay. Now suppose that we're looking at this periodic square wave, right? So we have this square wave going from minus t1 up to t1, and this is repeated every capital T. Okay, this is repeated every integer multiple of capital T. So this is a periodic signal, right? So over one period, mathematically over one period, okay, let's say from minus t over 2 to t over 2, you can express x of t in this form here. Okay, so x of t is 1 for t between minus capital T1 and T1, and 0 otherwise. Okay. Now, let us suppose for now that this signal has a Fourier series representation. Okay. So let's suppose that the Fourier series representation exists. Okay. So if the Fourier series representation exists, we can then find it using this formula here, okay, or this formula down here. So, right. So maybe let's start by looking at the case where k is equal to 0. So in this case, a0 is 1 over t, the integral over one period. Let's choose this to be minus t over 2 to t over 2, okay, of x of t dt. Okay. Now x of t is equal to 1 from minus t1 to t1. Okay, so this becomes 1 over t minus t1 to t1 dt, which is 2t1 over capital T. Okay, so the constant term, right? The constant term is essentially the average of the signal over one period. Okay. Okay. Now we can look at a more complicated case where k is not equal to 0. Okay. So if k is not equal to 0, then okay, let's see. You need to take ak equal to 1 over t integral x of t e to the minus j k omega naught t dt. Okay. Now this x of t, again, is just 1 between minus t1 to t1. So you can replace x of t with 1 and limiting the integral from minus t1 to t1. So if you do that, then you're just integrating over this complex exponential over this region. So what you get is this minus 1 over j k omega naught t e to the minus j k omega naught t from minus t1 to t1. Okay, so if you plug this inside, you get this with t1 minus the same thing with minus t1. Okay, so by Euler's formula, this gives you 2j over j k omega naught t1. Oh, I'm sorry. This should be, okay, this should be capital T here because of this. Okay, so this is 2j over jk omega naught capital T sine of k omega naught t1. Okay. Now, by the fact that omega naught t, by the fact that omega naught is 2 pi over capital T, okay, so if you plug this inside, right, this reduces to 2 over capital T sine of 2 pi over capital T k T1 over 2 pi over capital T k. Okay. So, right. Let me just write a T1 here and a T1 here. Okay. So if you look at this formula, right, so in the numerator, you have this sine function, right? And in the denominator, you have this term that is equal to the inside of the sine function. Okay. So this is basically okay. So this is basically what we call a sinc function, okay? That is defined as sine of x over x. Okay. So when x is at integer multiples of pi, right? If x is at integer multiples of pi, then sine is equal to 0. Okay. So if okay, if x is at integer multiples of pi, then sine is equal to 0. Okay. Except for the case where x is 0, right? So if x is equal to 0, then both the numerator and denominator are 0. Okay, so then you would have to apply L'Hopital's rule by taking the differentiation of both the numerator and denominator, in which case it will be equal to 1. Okay, so in general, for a sinc function would look something like this. So a sinc function would look something like this. It will be equal to 1 for x equal to 0, but it will be equal to 0 at integer multiples of pi. Let's say pi, 2 pi, 3 pi, and so on and so forth. Okay. Now, a sinusoid oscillates between 1 and -1, right? But as x increases, 1 over x becomes smaller and smaller. So you would see a signal that oscillates between positive and negative, but gradually decreases as x increases. So a sinc function would look something like this. Oops. Okay. So you start from this point, you go to 0 at pi, back to 0 at 2 pi, then 3 pi. So this is pi, okay. And then again to 0 at 4 pi, and so on and so forth. Okay. Right. Now, if you look at this, what this is essentially sampling a sinc function. Right. So this is essentially sampling the function 2t1 over t sine omega t1 over omega t1 at integer multiples of 2 pi over capital T. Okay, so you can view this as sampling this sinc function, okay, at integer multiples of 2 pi over T for omega. Okay. So you can see here that this sinc function here is scaled by T1, right? So instead of looking exactly like this, it is scaled by T1. Okay. So when you scale by T1, this means that you're sort of fast forwarding the signal, so the signal shrinks by 1 over T1.